Have you ever just stopped and wondered what holds literally everything together? I mean, from the water you drink to the very air you're breathing right now, our whole world is built on these invisible connections between tiny atoms. So today, we're going to pull back the curtain and look at that invisible glue that shapes our entire universe, the chemical bond.
So what is this fundamental force, really? Why do atoms even bother linking up in the first place? I mean, why don't they just float around by themselves? Well, the answer, as it turns out, is surprisingly simple, and it's the driving force behind pretty much all of chemistry.
It all boils down to a universal quest for one thing: stability. Just like a ball will always roll downhill to find its lowest, most stable energy state, atoms form bonds to do the exact same thing. This endless search for stability is the engine that makes all of chemistry run.
Okay, so our first mission here is to really get the why. What is it about being bonded together that makes a group of atoms so much more stable and, content than those same atoms just flying solo? And what's so fascinating is that when you look around in nature, you almost never find elements just hanging out as single atoms. The big exception? The noble gases. We're talking helium, neon, argon. They're kind of like the antisocial introverts of the periodic table. They're perfectly happy all on their own. But every other element, there's social butterflies, and they have to bond to find that stability they're looking for.
So what's the secret sauce for these noble gases? Why are they so special? It's all about their electrons. See, they have a completely full outer shell. That's their outermost layer of electrons, with exactly 8. And having this full set is an incredibly stable state to be in. This leads us to the absolute golden rule of bonding, the octet rule. Basically, atoms will do just about anything: give, take, or share their outer electrons just to get that magic number of 8 and become as stable and satisfied as a noble gas.
So, to hit that magic number 8, atoms have come up with two main strategies. It really just comes down to a simple choice. Do you give an electron away completely, or do you try to work out a more, let's say, cooperative sharing agreement?
And this brings us right to the two main types of chemical bonds. First up, we've got ionic bonds. This is a total transfer. One atom literally gives an electron away and another one snaps it up. Then we've got covalent bonds, where two atoms decide, hey, let's just share electrons, and they form this cooperative link right between them.
A perfect example of an ionic bond is something we all have in our kitchen: table salt, sodium chloride. So sodium has this one lonely electron in its outer shell that it is just desperate to get rid of. And chlorine? It has 7 and just needs one more to hit its magic number. So sodium gladly hands over its electron to chlorine. Now sodium's a positive ion, chlorine's a negative ion, and that opposites attract force is what holds them together. Bam! Both atoms are now stable and happy.
But what if you have two identical atoms, like two chlorines? I mean, neither one wants to just give up an electron to the other. So what do? They compromise. Each chlorine atom shares one of its outer electrons with the other one. By sharing that pair, they both get to count those electrons toward their total of 8. It's a total win-win, creating a super stable chlorine molecule through a covalent bond.
Okay, so we've got this idea of giving and sharing electrons, but it's a little abstract, right? How can we actually see it? How can we map out where all these electrons are going? Well, lucky for us, chemists came up with a brilliantly simple tool for that.
They're called Lewis structures, and you can think of them as the 2D architectural blueprints for molecules. They use simple dots to show the outer electrons and lines to show the bonds connecting the atoms. Honestly, they're an incredibly useful way to get a quick snapshot of a molecule's basic layout.
Let's try building one for a molecule we all know and love: water, H2O. First, we count up the outer electrons. Oxygen has 6, and each hydrogen has 1, so that gives us a grand total of 8. Next, we put the central atom, oxygen, right in the middle and draw single bonds out to the 2 hydrogens. Okay, that used up 4 of our electrons. The last 4? We just place them on the oxygen as 2 lone pairs. And just like that, you've got the blueprint for water. Pretty cool, huh?
Now, these 2D blueprints are fantastic, but they do have one pretty big limitation. Molecules don't actually exist on a flat piece of paper. They live in 3-dimensional space, and their 3D shape turns out to be absolutely critical for how they work.
For example, let's take methane, CH4. The Lewis structure is super simple. It's just a flat cross with carbon in the middle. It looks really neat and tidy, and it perfectly satisfies the octet rule for everyone involved. But this flat drawing is definitely hiding the real story.
So that's the big question, right? Is this flat plus sign shape really what a methane molecule looks like? If we could shrink down and see one, would it look like that? And the answer is a big, resounding no way.
To figure out the real shape, we use a concept called VSEPR theory. I know, it's a mouthful, but the idea is actually super simple. All those electron pairs are negatively charged, so they push each other away. They will automatically arrange themselves in 3D space to be as far apart as physically possible, to keep that repulsion to a minimum.
And this simple rule of repulsion is incredibly powerful. It means that the number of electron groups, or domains, around that central atom can reliably predict the molecule's basic shape. So if you have 2 domains, you get a straight line, 3 gives you a flat triangle, and 4, that gives you a 3-dimensional shape called a tetrahedron.
So, back to our methane molecule. With its 4 bonds, the only way for those electron pairs to get as far away from each other as possible is to point to the corners of a tetrahedron. This creates this beautiful, symmetrical 3D shape with bond angles of exactly 109.5 degrees. So, yeah, not flat at all.
But VSEPR theory has one more really fascinating little twist. What happens when some of those electron groups aren't actually involved in bonding? I'm talking about those lone pairs we saw in the water molecule earlier.
Let's go back to our water molecule for a second. The oxygen in the middle has 4 electron domains around it, 2 bonds to hydrogen and those 2 lone pairs. So based on the rule we just learned, it should have that perfect 109.5-degree tetrahedral angle, right? But experiments show us it doesn't. So what's going on here?
And here is the key detail. Not all electron repulsions are created equal. Lone pairs are only held by one atom's nucleus, so they're more spread out. They take up more space. You can kind of think of them as the bullies of the electron world. They push other electron pairs away much, much more strongly than bonding pairs do.
So in the water molecule, those 2 big, bulky lone pairs on the oxygen atom are literally pushing down on the 2 bonding pairs. This extra repulsion squeezes the HOH bond angle, compressing it from that ideal 109.5 degrees all the way down to about 104.5 degrees. And this is exactly what gives water its iconic bent or V shape.
And that simple little bend has enormous consequences. It's what makes water a polar molecule, it's what allows ice to float, and it's what makes life on Earth even possible. It's just amazing to think that from the tiny bend in a single water molecule all the way up to the double helix of DNA, these simple rules of attraction and repulsion are literally what build the entire architecture of life.
Of course, we've only just scratched the surface today. Chemistry is just filled with even more complex and beautiful 3D geometries that these simple rules create. Which kind of leaves us with a final thought. What other amazing molecular shapes are out there? And what incredible jobs do they have? All built from these same, simple, powerful rules.